of related papers because it both involves networks, statistical methodology, but also some optimization and approximation results. So thought that could be interesting, something for everyone. So what I'm going to talk about is seeding with limited or costly network information. So the idea is that we're going to be intervening in a network in particular, trying to spread some product adoption or behavior. And we're going to do so without necessarily observing the full network, which I think is going to come up in a lot of realistic settings. And so this is based on two papers, one that's forthcoming in Management Science and another that's a working paper. And Amin Rahman, who's my co-author, is actually joining us today in case there's any hard questions about some of the approximation results in the second half of this talk. I'm sure Amin will set us straight. So cool. So to give you a sense of the basic setup, the idea is that we have some network, and you can imagine a small network like this. And for each possible seed set, here seed sets of size 2, we could think about what's the total spread that would result in that network from seeding those two individuals. That could be intervening with some marketing intervention, giving them a free product, that kind of thing. And so given that maybe we infect these two people and there's some social contagion process that spreads from there, who eventually adopts. And so, one version of this topic is formalized in the influence maximization problem, where we try to find the best K nodes to maximize expected adoptions. And so we're going to consider kind of variations on this problem that arise when we don't necessarily have all the network data, right? So we often don't get to observe the network for free, right? Maybe in my past life at Facebook, maybe there we kind of already have the network for us. But in many interventions, we don't get the network for free, or if we do observe a network, it might not be the right one for the purpose of whatever we're interested in spreading. So interventions should kind of account for the cost that it takes to measure a network. Often, if you think of the network as costly, you're going to end up sort of sampling some parts of the network. And so you're not going to have the complete network information, but you may have some kind of complex random sample from the network. And so then if you have interventions that are based on that, those interventions themselves are going to be random in some ways because they're a function of this sampled subgraph. This is going to have some useful implications for empirical evaluations of these methods. And that's kind of the first paper that I'm going to talk a little bit about. And then under some assumed models of contagion, so if we assume that there's a particular type of spreading process, which is what has been common in a lot of the literature on influence maximization, there's actually some things that we can do to intervene to seed in the network in ways that provide us approximation guarantees. So how much do we lose from not knowing the full network? How close are we to optimal seeding? How close are we to seeding using full network information? And so all of this kind of leads to a framework where we can think about collecting some varying level of network information. So we could collect enough network information to have good interventions, good enough interventions. Cool. So, and of course, I'm happy to take questions at any point as we go along and discuss bits of this in more detail. Okay. So to make this a little bit concrete, here's a network that is a village in rural Honduras that was measured by Kim et al. 2015, which is a paper in The Lancet. They were trying to spread some health-related product adoption, in particular multivitamins and a water purification method. And so they measured social networks for these villages in rural Honduras, and they had in mind that, okay, we're measuring these networks as part of this research, but if we were going to really roll out these interventions, we want to do this in a way that doesn't require measuring the whole network. And so they were contemplating, how can we do that? And so in particular, one of the seeding methods that they consider is one that we're going to call one-hop, sometimes also called acquaintance sampling, nomination targeting, or friendship paradox targeting, where the idea is that you randomly sample K individuals, and then for each one of them, you randomly sample one of their neighbors. And that network neighbor you select as the seed, okay? They also considered a version where they just picked people entirely at random as seeds. And then also, given that they had measured the full network, they did do targeting based on the maximum in degree. Okay. And so here in this one particular network, we see the nodes that were selected for these two different interventions that were happening in that network. Okay. So this is, already highlights a couple ways you might try to seed in a network without knowing the full network information. First, you could just have no network information at all and just randomly seed, right? Another approach would be maybe we have very local network information. We use this kind of one-hop mechanism where we pick somebody at random and then we pick one of their neighbors at random. The idea here is to exploit a version of the friendship paradox, whereby your friends have more friends than you do on average. And so the hope is that by picking somebody at random and then picking one of their neighbors at random, we're going to be moving to people who are higher degree and more central in other ways, and who are going to be a more effective seed set. Okay, this was actually originally proposed in the context of vaccination, but has also been thought about in the case of seeding that we're considering here, and also sensing in the network, right? So this one-hop seeding seems like an interesting approach that doesn't require this full network information. Now, I'd say there are some limitations to it. It doesn't really pool information in any way. So even though we've talked with K people about who their neighbors are, and at least one of their network neighbors, we don't pool that information in any way. And it doesn't necessarily offer any particular guarantees about its performance, even under an assumed spreading model. And so, for example, if we were in this network on the right that has this tree structure, we would really like to seed this this root node potentially if we if the contagion is occurring with high probability, but we won't necessarily actually do that. Now, one of the things that's interesting about this one-hop seeding method is because it's just involves sampling these K nodes at random. This results in a stochastic strategy, right? So it's not that this is always going to pick the same set of nodes as seeds. It's going to pick a different set depending on which K people we pick and which of their neighbors we pick then to be seeds. So, for example, again, this same network, this is a network of households in rural China. And so we could see that there are these two red nodes, and those are the two nodes that actually have the highest probability of being selected under this one-hop seeding, right? Because many people are naming them, right? And that's shown in this distribution to the left, right? There's these two blue nodes, and if we're selecting, two seeds, then this pair of nodes has some, pretty substantial probability of being selected. It's one of the more probable pairs of nodes that we might select. Meanwhile, this green pair of nodes is not so probable. And you can kind of see that one of the green nodes is only named by one person. So in order to select that set using one-hop targeting, we would have to have picked this particular neighbor as our starting point, and then randomly followed this edge in order to select this person, okay? So some seed sets are more probable, some seed sets are less probable, but this seeding strategy actually puts positive probability over a lot of different possible seed sets, right? So the fact that this is stochastic is actually kind of an interesting feature of this seeding strategy, right? And if we, in fact, look at some of the seed sets that were selected in this Kim et al. Study in rural Honduras, we can see that sometimes this happens. So here, the red seeds on the striped ones are the random seed set, and the green is the nomination, or what we're calling the one-hop seed set. And we see in this case, it looks like the one-hop seed set that was selected in this village. I think one of these was selected for multivitamins and the other was selected for water purification. This one-hop seed set in green is more central to the network, okay? But this need not always happen, actually. So across the villages in Honduras where one behavior, multivitamins, for example, was seeded using a random seed set, and the other behavior, say the water purification, was seeded using the one-hop method, actually 3 out of 8 of those villages, the random seed set ended up being the higher degree seed set than the one-hop seed set, right? Because certainly random is a stochastic strategy. It puts positive probability over all seed sets of size 2, right? And the one-hop strategy puts positive probability over a lot of seed sets as well. Here in this distribution of the probability of each seed set of size 2 in this network, this dotted line is the random uniform probability over all the seed sets, okay? So the fact that these seeding strategies are stochastic is interesting, right? I mean, this is just going to be a nature of making decisions based on sampled information. In fact, one of the nice features of this is going to allow us to empirically evaluate these seeding strategies, even in field experiment data that was not selected for this purpose, okay? Because we can compute these probabilities. So, and I already showed you sort of one computation of that, but just to make sure that you kind of understand how this one-hop strategy works, let's say we're just picking a single seed. So k equals 1. We're just selecting one seed. So then the probability of selecting a particular node as our seed depends on how many people name that node and how many people are those people name who are not that node, right? So what their out degree overall is, right? If somebody names me and I'm the only person they name as maybe somebody that they discuss matters of personal finance and farming with, then if they're selected, then we'll obviously follow this short random walk to me. Okay, so it just depends on this kind of out degree normalized in degree. Okay, and that's shown sizing these nodes on the left, right? So some of them are much more likely to be selected according to the one hop than others. Okay, so we can in fact use this fact that these strategies are stochastic and that we can compute the probabilities of any particular seed set being selected in order to do some essentially off-policy evaluation of these seeding strategies. Okay, so even though a seeding strategy is something that's going to pick some set from all the sets of nodes, and so there's really this huge combinatorial explosion of options, these seeding strategies are actually putting a probability distribution over those sets, and so that's going to make it possible to do evaluation of them. So we want to do things like compare how one seeding strategy does compared with another seeding strategy in real data. So if we want to estimate the expected outcomes under 2 different targeting or seeding strategies, A and B, right, we're interested in, say, in a finite population, maybe a finite population of villages or firms or schools, right? What would the outcome be if we had used strategy A versus strategy B? And so that's what's written here, where our expectations are being taken over the fact that the seed sets, these SIs, are random variables because these seeding strategies themselves are stochastic. Okay. So we can similarly consider a superpopulation version of this, where just the expectations now involve sampling from this superpopulation, and also the fact that this how we're selecting the seed sets are drawn from these 2 different random distributions. One maybe that's one hop, and one perhaps that is this uniform random seeding. Okay. So one of the things to note about this quantity, which we can think of as a kind of average treatment effect, what's the effect of using strategy A versus strategy B, can also be rewritten in this form, where we're going to be weighting outcomes, the Y's, according to the difference in probability of that particular seed set having been selected by the 2 different strategies of interest. And then we need to normalize by the probability of that seed set under our design that we're going to denote with delta. So there's some way that we actually sampled seed sets in some data that we have, and we're going to use that data to try to evaluate how these seeding strategies work. Okay.
So Dean, can you remind us of the notation? What was Y and I here again?
Mm-hmm. So Y is the network level outcome. How many people or what fraction of people, depending on which you might prefer, adopt the behavior or product of interest. And I is indexing in the upper part is indexing the particular villages or schools or firms. And so we're going to think about a setting where we basically have many different networks that we're observing, and we're going to be doing seeding in each one of those networks and pooling information across all of them. So in this Honduras example, there's like 32 villages. We're going to have another example that's 150 villages in China. And so the outcome in each village is a function of the seed set selected in that village. Yeah. Okay, so given this kind of setup, essentially you can think of this as a case where we have some design distribution that we use to sample data. So if you imagine we ran a field experiment like what Kim et al. Did, where they randomly assigned some villages to one-hop seeding and some villages to random seeding, then our design distribution is a mixture of these two strategies, right? And that's giving us the probability of selecting a particular seed set given our design. And then we also know the probability of selecting a particular seed set under either of the two policies that we're considering evaluating. And so we're just going to denote these probabilities for the particular seed sets that we observe. That is these little SIs. We're just going to sorry. Okay, going to note those with AI, BI, and delta I for the probability of the particular seed set that we observed under the strategy A, strategy B, or under the design. So this last one, this delta I, you can think of this as being a design-based propensity score, right? Here, unlike in most causal inference settings, our treatment is this combinatorial thing because it's this set, and also we know the probabilities exactly, but this is a design-based propensity score essentially. So in order to estimate this quantity that we were interested in, this tau, which is the contrast between the outcomes under two seeding strategies, we can use inverse probability weighting estimators like a Horvitz-Thompson estimator. So in the Horvitz-Thompson estimator,
I'm sorry to cut you off. Back 2 slides ago, the row that's defining sorry, one more slide. There's this row that's defining the mixture.
Yeah.
So in the data that you're given access to, I would expect that they used kind of one seeding strategy. Here, are you assuming that they flip between two different ones, so you have enough kind of signal about the alternatives, or
right?
How should I think about this?
So in some settings, people are actually running randomized experiments to try to compare different seeding strategies. And so in Kim et al., like if you set aside this one seeding strategy that does use the full network information, they're comparing random and one hop, and they're basically flipping the coin to decide whether some village gets random or whether it gets one hop. So then, row could be 1/2. Actually, in the evaluations the one evaluation I'm going to show you, we have a couple in the paper. I'm just going to show one. In fact, we do all of this sort of off policy. And so the data that's generated is entirely from random seeding. So actually, that would be a case where it's all of the data is generated from policy B, which is random seeding. So one of the assumptions that we need is a kind of positivity assumption, that if we want to evaluate a strategy, then anywhere that it puts positive probability, we need to have had a design that also put positive probability on those same seed sets. So if our design is just random seeding, then we're going to have positive probability over all seed sets of some fixed size, and so we'll be fine, at least theoretically. Whether you are in practice, you might need a lot of data. You can see, for example, if we had a seeding strategy we're interested in that's not stochastic, that given a network, it observes the whole network and then picks always the same seeds, right? That's going to be very hard to evaluate with data from random seeding, because your chance of getting that particular seed set through random seeding is going to be very, very small, right? Because this is going to be 1 over all the possible seed sets, which there's a combinatorial number of. So, so in practice, we're going to sort of need something a bit more than that. But the basic assumption is that we had that kind of positivity.
Okay, makes sense.
Yeah,
that makes sense. Thanks.
Yeah. So yeah, so then we can do this kind of estimation. We're just going to take the observed Ys. So for each village, we observe what number or fraction of people end up adopting. And then we can use these weights, where these weights are just going to be the ratio between the probability of that seed set under the strategy of interest to the design. In the case where the design is random seeding, then in this case here, this is actually just going to cancel out this this BI over delta I. These would be the same. If the data was generated by random seeding and strategy B is random seeding, then those are the same value. In practice, we don't really use the Horvitz-Thompson estimator. I think any of you who've used, importance sampling, if you're coming from more that kind of Monte Carlo or computer science world, you think of these as importance sampling estimators. The one difference is that we're sort of comparing 2 distributions compared with a normal importance sampling estimator. Is that often you don't use the unnormalized importance sampling estimator, which in the survey sampling and causal inference world, we call the Horvitz-Thompson estimator. You use a normalized version of it. And so you just would say, set these weights so that they always sum to some constant. And that'll stabilize the estimator. But it's essentially the same idea. And so we're going to, in most of the results I'm going to show you, going to use this Hayek estimator, which just normalizes these weights. This is like the normalized importance sampling estimator. Okay, so how does this actually work in practice? And so maybe to make this more concrete, let's look at a reanalysis of a particular data set. So here's this experiment by Jing Tsai and colleagues, where they were basically marketing farmers insurance in 150 villages in China, where these households are engaged in rice farming. And so the government was very interested in basically getting rice farmers to have insurance. And so the treatment here is intensive information, an intensive information session about this insurance product. And that this occurs in an earlier time period. Some households will later get the same information, but we're focusing on which households got this information in an early time period. That's going to be the seed set. And then our outcome, the Y, is going to be the fraction of adopters in a village. What fraction of the village ends up buying this insurance product? So in this case, all villages were actually assigned to a uniform random strategy, right? So it was just who got this early information session was determined at random, but our method is going to allow us to do off-policy evaluation. So we're going to be able to compute what the mean outcome would have been, not only under this random seeding, but also under other seeding methods. In particular, we're going to look at this one-hop seeding. Okay, so here's how we do that. So each point in this plot on the left is one village and the seed set that was observed in this actual data, the set of households that were targeted with this intervention. And so on the x-axis is the probability of selecting that seed set under the random seeding strategy, which also was the design of the experiment, how these seeds were really selected, okay? And there's some variation here, but this variation is entirely driven by the size of the village and the size of the seed set, right? Because all seed sets of the required size have the equal probability. The number of seeds that was selected varied from village to village, but fixing that, the probability of selecting a particular seed set is the same. So that's all the variation that's happening on the x-axis. Then on the y-axis, I've plotted the ratio of the probability of selecting that seed set under one hop to its probability under random. And so there's going to be a bunch of variation in, we happen to select these 2 particular households. What's their probability of having been selected if we had been using one-hop seeding, right? So if we kind of go back to this picture and we say we happen to observe that in this village, the two blue nodes were selected as seeds. They were selected under the random distribution over seed sets, but we can compute that under the one-hop distribution, maybe it looks like they have about twice the probability as they would have under random, which is this this line here, right? And so that's essentially what is being plotted here, right? And we can see that there's a substantial number of seed sets, that is villages with an observed seed set, where that seed set is more probable under one hop than it is under random, right? So, and this variation, this vertical variation, is this variation that's going to allow us to actually evaluate, how does one hop compare with random, even though this data is combinatorial and arises from just random seeding, okay? You can see that there's some villages that have seed sets that have 0 probability under one hop, and we've superimposed those at the bottom, even though this is on the log scale. So they should be way off the bottom, right? Why do those have 0 probability? Well, those probably involve, well, this is exactly what happens, which is that those involve seeds that no one names. So in the underlying social network data here that's asking people to question, who do you discuss matters about personal finance and farming with, no one names those households. So it's impossible to select those households as seeds under one hop. Okay. So now that we have these weights, we can look at those weights in combination with the Ys and compute a mean under one hop and a mean under random, and in particular, the difference in means, that tau that we're after. And that's what we have on the right here. And so for random, the weight that we give to each village is the same, because all these weights cancel out, right? Because our data is coming from random. Under estimated mean take up under these two different ways of seeding, random and one hop. So if you're looking at this and maybe following along, you might be thinking, why is it that the random line is to the right of the one hop line? Does that mean that the mean take up is higher under random than this one hop strategy that was supposed to leverage the friendship paradox for us? And yes, that's correct. So basically, our point estimate is that the effect of using one hop rather than random would be to decrease adoption in these networks. Now, I would say this is sort of not super strong statistical evidence. Our analytical p-value here is like 0.04, and a p-value that we get from doing a kind of variation on a permutation test that will perform better in this kind of finite sample is a little bit less than 0.1. So this isn't super strong evidence, but certainly we're not seeing evidence that this one hop strategy is performing really well here. Okay, so there's more on this in this first paper. We do a couple more evaluations and similarly are not finding really promising results for one hop, though some other authors, such as these folks who wrote this Lancet paper in Honduras, have found more promising results from one hop. So one thought here is just, in some ways, this suggests that random seeding is pretty good, right? And in fact, this is an argument explicitly advanced in a recent paper by Mohammed Akbarpour and colleagues at Stanford, where they say network information is worth just a few seeds more. In particular, if instead of seeding k nodes using the full network information, we just seed a bit more than k nodes at random, we might be able to outperform the version leveraging the network information. Now, some of their results require some particularly strong assumptions for this setting, including that the network is drawn from a particular random graph, and in particular that their results for directed graphs are quite restrictive, and we might think directed graphs are really important to studying seeding and influence, right? So this just sort of raises this question of, okay, in some ways we had this idea that we could just do seeding at random. How far can we get there? And then maybe we can do things with the whole network information. And then what I've suggested so far is actually that we could do something like one-hop seeding, where we have just some very local information, right? And at the other end, we have just a full knowledge of the network, and that's kind of the standard influence maximization problem. So what we try to do in the second paper that I'm talking about here is this idea that we could explore the space between no information and full information, and perhaps actually offer some guarantees about how well we can do even with this limited information. Okay, so this is going to now be this part of this talk that gets more into actually construction of new algorithms for seeding that control how much of the network information we need to collect, but maybe are going to be better than this one-hop strategy that tried to limit how much information we collected, but might not work for various reasons, including even under an assumed model of spread. Okay, so formally our problem here is this K influence maximization problem. We're trying to find the K nodes to maximize the expected adoptions. So this problem is NP hard. What generally this literature has done is looked at cases where it turns out that this influence function, the expected number of adopters given some seed set S. So here, this is sort of stating this problem, right? Is that we'd like to, given some seed set size, we want to find a seed set that maximizes the spread. Then we're going to use some kind of approximation to this, and that this influence function is often going to be submodular in some of the models of spread that we're interested in. Okay, typically, then this is in a setup where we assume that we have access to the whole network. But we're going to say, what if we don't actually have access to the whole network? What if we're going to have to query the network in some way that corresponds to how often these networks are learned about in practice? So the particular setup we're going to look at, and there's a little bit more variations on this in the paper, we're going to be considering a contagion model where there's this independent cascade. Each edge in the network has a one-time chance to pass adoptions with probability P. So if your neighbor is infected, then they can infect you in the next round with probability P, and if they don't do that, then they never will. This you can think of also as an SIR model, where there's a deterministic transition between I and R. Okay, and then our focus is we're going to have limited access to the graph structure through queries. Okay, and then the results that we have here are that we have these new algorithms that are going to provide some tight guarantees for general graphs using a bounded number of queries. And this will also allow us to sort of quantify really the value of network information in a smoother way. How much do we learn about the network and how valuable is that? Okay, so the general approach and kind of the intuition here is that instead of optimizing the influence function as we do in influence maximization on the whole network, we're going to do that on a sampled subgraph. Now, how do we sample the subgraph? We're going to generate this sampled subgraph through something that is like the spreading process itself, or often some version of it running in reverse if we care about directed graphs. Okay, and so we're going to consider in particular two query methods. One that I think helps build some of the intuitions here and could be useful in some cases, influence sampling. So this is where we'd see somebody seed a random node and then see the set of eventual adopters. We actually don't need to see the whole path of adoptions. We just see who eventually adopts. So this could be applicable when prior cascades are observed, or maybe you can cheaply seed one behavior and you're preparing to seed some other behavior later. The query method that I think we're most excited about and that we emphasize the most in the paper is edge queries. So we're going to be able to look at a node and observe a random neighbor of that node. Okay, this is often used in sublinear algorithms in the context of doing computations in graphs. It also is going to show up as something that looks like what we might do in real data collection. First, these kinds of snowball or respondent-driven sampling like surveys in the field. People go around, surveyors go around with a mobile phone app. One of the ones that has been built is called Trellis, that allows you to basically ask people who they know and try to do name disambiguation, et cetera, right? And this is an expensive, time-consuming process, right? This could also cover something like crawling an online network where we may have rate limits. We can't just crawl all of Twitter this weekend, right? Okay, so let's first look at this kind of influence sampling. So in influence sampling, the idea is we're going to pick some node at random, this red node, and then run this spreading process, right? So we've actually seeded that random node, and then we see who eventually adopts, right? So each query consists of seeding a single node, and then what we get is the identity of who ended up adopting. So we can then use the identity of the adopters from these independent cascades in order to figure out how to do seeding of K nodes later in sort of the real thing that we're trying to spread. Okay. So if you say imagine looking at a case where we did this 3 times. So at the top we did one spread, and then we seeded another node at random in blue, and that resulted in that spread. We seeded another random node that's in orange, and that spread, right? We can now think about, okay, 2 different nodes that we could pick as a seed, the green one or the black one. Well, let's look at how many times each of those show up in the adopter set. Now, if we're in a symmetric influence setup, so this is an undirected network, and there's no kind of different weights in different directions on the network, then we can actually just look at that by looking at how many times the green node and the black node show up in these different cascades, right? And so to value the first node, we just would pick the node that shows up in the most of these cascades. Then to pick the second node, we're going to avoid redundancy, discard the cascades that were already covered by the nodes that we've already put into our seed set. So this is not unlike what one does in this kind of greedy influence maximization algorithm where you're trying to avoid redundancy. Okay, now I would say one of the big limitations of this kind of approach where we sample a seed and then see its eventual spread is that this assumes that the network is undirected. And as I just said, that was sort of one of my complaints about the Akbapur et al. Results, right? Is that realistically, in the case where we care about influence, we think that the network is much more directed and that it's important not to neglect that, right? I might pay attention to Oprah. Oprah's not paying attention to me, right? So just because I'm here showing up in all these cascades because I'm paying attention to a lot of things doesn't mean that seeding me would be a way to influence all those same people. Okay, so there are some nice results there, but I'd say overall we think this helps build some intuitions about the idea that we want to run some kind of spreading process. In particular, to handle directed networks, we need to be able to run the spreading process in reverse. Now, in the context of actually surveying and crawling, we can do that. But that requires maybe reformulating what the query method is a little bit. So the query method that we focus on the most is edge queries. We query a node simply by asking it to reveal its edges with probability P independently at random and proceed to query its neighbors, etc. This is the same P as in our spreading model, right? Though we consider some robustness to these 2 probabilities not matching. So that is starting from a random set of initial points, we obtain multiple sub-sampled copies of the original graph. And then we're going to do something like what we just did before, okay? So here we might start from these 4 different nodes in solid red, and then we're querying the network from them. Then we do the exact same thing again, but we're following different edges. And again. Now, in practice, we don't actually have to do this multiple times. The surveyors would have an app, right? And they can be following multiple edges from the same person, right? Our crawler can implement this without revisiting things. It can sort of do this computation all in parallel, okay? So the idea is that we're observing these random neighbors. And this shows up in these kinds of settings. So again, we're going to get these multiple copies of having started at some fixed set of points and then randomly following some of the edges. One thing we do is also have some ways of controlling how far this goes. Once the connected component we reach is some size, we can stop. Right, so that we don't, if we hit this one supercentral node, we don't just end up covering the whole network immediately. Okay, so in order to evaluate how good a particular seed would be using this data, right, we're going to look at the number of reachable initial nodes. And so here again, we're going to evaluate these two nodes as potential first seeds. If we just have, k equals 1, say, then we want to look, okay, the green or the black node. And so in this first sample, the green node just can't reach any of the initial nodes. The black node can reach one of the initial nodes, and we can keep track of direction in all this, right? Then, can reach 3 of the initial nodes, and then in the next case, both of them can only reach 1, and in the next case, both of them can reach 2. Okay, so we're going to prefer this this black node as our initial seed if we're just picking 1, right? Or we're doing this greedily. So we're gonna, if we want k greater than 1, we're gonna pick this node greedily, and then we're gonna remove the initial nodes that are already covered. Okay, so how well does this do? What can this guarantee for us about finding a seed set that is not so far off of optimal, or not so far off of what we could get if we knew the whole network information? So it turns out this is hard. And so we have some hardness results, and it's helpful to look at this network here. So if you think about, we have a network that just consists of a bunch of clicks, and then some of the clicks are connected by a single edge into a ring like this. So we really want to seed the set of clicks that have been modified to be connected with each other, right? But in order to do that, we're going to end up having to sample quite a bit of the network. Okay, so this is going to provide a lower bound on how many edge queries we have to do, and so that's kind of the disappointing hard result here. And so our approximation guarantee with a bounded number of edge queries is going to involve this order n additive loss. There's going to be some epsilon n factor, additive factor, that we're off from the optimal by, or in particular, we're off from the greedy approximation to the optimal. So, so this is a difficult problem, and I think one of the things to note about this, the fact that we have this epsilon n additive loss, is that this means that this is going to be most informative and provide the best guarantee when we're actually considering contagions that are going to reach some order n number of people, right? Otherwise, maybe this result is not as informative. That's also true in the Aquapoor results, is that they're also considering contagions that reach a lot of people, right? We're talking about contagions that don't actually spread very far in the network, right? That are, some kind of vanishing fraction of the network. Then maybe this guarantee is not as helpful. But I think it's we're quite happy with the fact that we were able to say anything about this worst case result for any graph.
Sorry, can I just ask a quick question? What here n is the number of nodes, and right?
Yes. Yeah. So sorry. One thing, and I think I saw you in chat about that. In the first half of the talk, n was the number of distinct networks. Here we can do this with a single network. If we want to do empirical evaluations of it, we might need multiple networks. But here n is going to be the number of nodes. Yeah.
And what is p and rho?
So p is the probability that governs the contagion. So that each adopter neighbor has some probability p of infecting you in this one time, and then and then we also have capital T, which is the number of independent copies that we have. So in this example that I gave you here, we're going to have 3 copies, but in practice, we might want more copies than that, right? So the multiple times that we sort of follow this random walk from these same starting point nodes. And then rho is the fraction of the network that we're using as those initial starting points. And so n rho is the number of starting point nodes. So in this example that I showed earlier here, n rho is 3. Sorry, is what is it? 4 here? No, 3. Yeah.
Okay, but then the number of edge queries is still n squared, but there's order n squared edges, so I'm sure I feel like I'm probably missing something. Is the idea that maybe this idea of sampling is easier in practice than just asking every pair of people if they know each other?
I can add a few just quick things here, that the number of edge queries is actually Pn squared. So the previous hardness result shows that we cannot achieve using any subquadratic edge queries. Now, if we take P to be log n over n, then we are actually querying using n log n edges. And we have a second hardness result that shows we cannot provide mu opt minus epsilon n guarantee with anything less than Pn squared edge queries. So the dependence on P is actually optimal here.
Mm-hmm.
The order dependence on P.
And in a bunch of cases, practically P might be relatively small, right?
Okay.
Right. I mean, if you think about, like, you have somebody who adopts some product who's your Facebook friend, you have 1,000 friends. P could be quite small, and you could still have a contagion that's going to actually reach some order n number of adopters. Yeah.
I see. Okay.
Yeah.
Thank you.
Yeah. No, that's very helpful, and thanks, Amit.
Sorry, a quick question to follow up.
Mm-hmm.
So for the initial nodes that you choose for the edge queries, these initial nodes, they don't have to be in the seed set at the end, right?
No. Right.
Because there's been a lot of work on also like adaptive inference maximization, where you can observe the graph once you pick some nodes to be in the seed set, right? So that's the main difference with that line of work.
Right. So yeah. So we're thinking instead that we're just sort of trying to use this to probe the network. Yeah. These need not be people that we seed, and in fact, the thought would be is maybe less expensive to just be talking with them than actually choosing them as a seed in a bunch of cases where there might be an intensive informational intervention. So I'm just going to wrap up by showing a little bit of an empirical exercise, some simulations in the University of Pennsylvania Facebook social network. So we just looking at this one network, you can think about how we can trade off how many seeds we have versus how much querying we do. So on the x-axis here is T, this number of copies that we take from these 100 initial starting points, right? And so this has the consequence of controlling what fraction of the edges that we're querying, maybe 40%, et cetera, right? And what's going to start out the best when we don't use any information, we're just doing random seeding on the far left, is when we have a larger seed set size, k equals 10, right? But we can see here that there's some point at which actually by querying some, but not all of the network, right, we're able to reach the same spread size with a smaller number of seeds, okay? And so one consequence of that is if you think about there being some cost associated with the cost per seed and then a cost per query iteration, there could be some interior amount of querying the network that is best. Now here, that's not necessarily the case. So here, if seeding is half the cost of running one of these query iterations, then you're going to conclude that what you should probably do is do almost no querying and just have a lot of seeds. That's kind of the Akbat-Poor result. However, if, say, seeding is twice as expensive as one query iteration, then you're going to start to get these kind of interior maxima here, where our profit is going to be maximized accounting for these costs by querying to some degree, right? And so it's actually going to be best for us to run, say, 15 copies of this querying process, which can be done in parallel, and then choose 2 seeds as a result of that. Okay. And so that's kind of the idea, is that this whole setup is going to allow us to, if there's costs associated with seeding, to consider collecting some, but not all of the network information. So just to wrap up, basically, in general, I'm trying here to explore the middle ground between complete and no information about networks. There's some interesting heuristic seeding strategies here, one hop, but they may not always work out. So we've proposed some new algorithms that can give us some approximation guarantees and are a bit more powerful in terms of how they use, and combine information from probing different parts of the network in order to seed. And this allows us to also kind of consider the diminishing returns of network information and the benefits of collecting just some network information. So thanks a lot for your questions, and happy to discuss more and talk with you all more today. So these are the 2 papers. The first one is this more statistical paper that's forthcoming in Management Science, and the second one is this more algorithmic paper that's with Amin. Thanks.